Okay, so thank you for coming on this time of the morning. This is a joint work with Robert Krauthgamer, who is already on his way to Israel, and Barna, Saha, who is here. So I'm going to talk about sublinear time algorithm for edit distance. So first, let me define the problem. So edit distance is a measure of defining distance between strings. So if I give you two strings, say of the same length, we will call it n, over some alphabet sigma, then their edit distance is the minimal number of edit operations needed to convert x into y. So what do we mean by edit operations? We can do bit insertions, we can do bit deletions and bit flips. Soon we will see an example. And this is a very basic measurement of distance, and it's used in many, many applications, including computation and biology, pattern recognition, text processing, and many else. So let us do a very quick example just to demonstrate the definitions. So if I give you these two strings, x and y, how can we convert x into y? So this is x, then we first delete the first bit of x. Then we can do a substitutions. We just convert d into c. And finally, we append a to the end of the string, and we get the string y. So you can see that the edit distance between these two strings, x and y, is 3. So, okay, so this is a nice measurement, but how about algorithms? How much time does it take to compute the edit distance between strings? So we have a very classical dynamic programming for the problem from the 70s that solves the problem in a quadratic time. And there were some improvement, but we could only shave polylog factor of n, and we couldn't break like the subquadratic time. And actually, if you believe the strong ETH, then there is no such an algorithm. Like every algorithm, yes? Yes, but I don't want to get into this. I would like that just the takeaway message is that this is hard, and roughly the best you can do is a quadratic time to save the exact problem. So if that is the situation for the exact problem, then naturally the problem, the approach of approximation arises. So what you can do by approximation? So there was a very long and extensive research on approximation algorithm, starting from a square root of n approximation factor in linear time. And the very recent results provide order of 1 approximation, either in subquadratic time. And if you afford to have like not a good constant approximation, then we can also do it almost in near linear time. So okay, so how about sublinear time? If we are happy with the linear time algorithm, can we do it in sublinear time algorithm? So first, let us state what we aim in sublinear time algorithm. So we would like to solve what we call the K1, K2 gap problem. So given two strings, we would like to decide whether their edit distance is smaller than K1 or larger than K2. If it is somewhere in between, we do not care what the algorithm outputs. So if we come back to the Hamming problem, to the Hamming distance, then we can solve the t versus c times t for any constant in time which is roughly n over t, okay? And the constant also hides, the big O notation hides the constant c. What about edit distance? So Batu et al. Have an algorithm that solves the n to the alpha versus omega of n gap in time, which I won't get into it, so it's some sublinear time. Then Andoni and Onak gave an algorithm that solves a better gap. And again, I'm not going to get into the exact running time. So these are the previous known results. And what is our new result? So we show that there exists an algorithm that solves the t versus t square gap in time, which is n over t plus t cube. So okay, so this is the main result. Let's try to compare it versus the previous result. So first, we want to demonstrate that our algorithm is sublinear when the distances are small. And in many applications, this is really the interesting case. Like when the distances are small, we would like to check whether it is very small or a bit larger. So this is what we can do when t is the little o of n to the third. Then we have a sublinear time algorithm. And actually, in this regime, Andoni and Onak have an algorithm that runs in time, which is superlinear. So in this regime, we are better. If we compare it to Hamming distance, then, okay, we are a bit inferior. Like in Hamming distance, we can solve this gap in time n over t square. We have n over t, and we have an extra factor of t cube. Okay, so that's the result. And now let me show you like a little bit just to taste how does what are the proof techniques we use. So let me start by a very simple algorithm that have asymmetric query complexity. It will query one of the inputs in n over t locations, but on the other hand, it will have to read the entire string y. So what do? We sample a subset of the elements 1 over n of size n over t. And then we apply the standard dynamic programming. Instead of every row, like what we do regularly, we just do it on the sample set of rows. So what do we mean by that? So for each row in the sample set of row, we have to compare xi against yi plus s, where s is all the candidate shifts. So if we are talking about distances which are up to t, then the candidate shift could be like between minus t and t. Okay, so this is like the first thing. If you think about the problem like for 5 minutes, maybe that's the first thing that you are trying to do. So what happens with this algorithm? So indeed, if we look on the first string x, then since we only compare rows that coming from our sampled set, so we are sampling it in n over t locations. But on the other hand, what happens to y? So for y, remember that we have to compare xi to yi plus s for all the candidate shifts. And since there are 2t candidate shifts, then we have n over t times 2t. Then we have to read the entire string y. So this algorithm indeed is somewhat sublinear. It is just querying x in few locations. But on the other hand, it has to read the entire string y. It is very easy to show. I will not show it here, but it is very easy to show that in this approach, we can solve the t versus t square gap in linear time. Okay, why in linear time? If you think of it, you have a dynamic programming, and the size of the table of the dynamic programming is just linear. So what was our main challenge? We would like somehow that for each sample, the row, we don't want to do like omega of t comparisons. We would like to do only order of 1 comparison. Otherwise, we reach a linear time algorithm. Okay, so that was our main challenge. And to see how we solve our main challenge, let's play a bit with the problems. So let's start with one toy example. So what happens if the first string x is just random? Yes, we just pick it at random, and we know that the edit distance between x and y is small.
This alphabet, because what should I think of the alphabet?
Think of it as 0 as a binary alphabet. Yes, it works for every alphabet, but think of binary. So then if x is random, then, and the edit distance between x and y is small, then for each row, there is only a single candidate shift s. We don't know it ahead, but if you think of it, there is roughly only one way to convert x into y. So there is only one candidate shift. If that is the case, then we can check whether xi matches the only candidate shift, and we can do it by sampling. So we don't have to match xi to all the possible shifts, since if we know the shift A, there is only one shift. So in the case that x is random, and maybe more specifically, if we know that there exists only a single candidate shift, then we can do well by sampling. So what happens in the other extreme? So in edit distance, like many times when we divide things, we say, okay, if the string is random, then we do one thing. Otherwise, we assume the string is periodic. So let's see what happens if the string is periodic. So suppose it's periodic with period p. What do we mean by that? We mean that for every index I, the value of xi equals the value of xi minus p. So in this example, like the 4th bit of x equals the first one, the 5 equals the second, and so on. Yes, so here the period is 3. Then I'm claiming that the possible matching shifts are p par apart. What do I mean by that? So I claim that if x and y are close, then y is also close to being periodic. And if y is also close to being periodic, then the first bit of x either matches the first bit of y, or the 4th, or the 7th, and so on, or it matches the 2nd, the 5th, the 8th, and so on. Yes, so the possible matching shifts must be p par apart. So does it save us? Like, okay, if they are p par apart, maybe there are much fewer possible shifts, but actually it doesn't help us, because if the period is very small, like in this example, if it is only of size 3, then we still have, instead of maybe 2t candidate shifts, we have it divided by 3. So we still have omega of t candidate shifts. But here is a very cool thing about period shifts, period strings. So suppose x is periodic, and now suppose that y is close to being periodic, but then at some point it deviates from the period. So here you can see that the red character doesn't match the period. Then I claim that that when y deviates from the period, it affects all the matching diagonal. So here it affects the largest diagonal. Then if we proceed like 3 rows, then it affects the second largest. After another 3 rows, it affects the third largest, and so on. So somehow there is a miracle, like we just see one deviation from the period, and somehow miraculously it affects all the possible matching strings. So then here is an idea. Instead of comparing xi versus yi plus s for all the possible shifts, we will just check that x and y are still periodic with the same pattern. So what do I mean by that? I will check that xi matches xi minus p, and yi matches yi minus p. So in picture, I will check that xi matches what it has to be 3 bits ahead, and then I see a period violation, then I know that all the possible shifts will have a mismatch. But now, if that is all what we do, we can check it by sampling. Instead of verifying that x and y are perfectly periodic, I will just check it by sampling. So also in this case, where this seems to be the hard case, we are on a good shape because we can still do things by sampling. So okay, so we have 2 examples, and in both of the examples we are fine, but what about the general case? So this is the Keylemma, which is quite informal, but it roughly says that if the edit distance between x and y is small, then it is either the case that we are on the first example, that there is only a single matching shift s, or it must be the case that both x and y are periodic with the same period pattern. And then again, we are on a good shape. So then, of course, we have algorithmic challenges. How do we verify whether we are on the first case or in the second case? If we are on the first case, that there exists only a single candidate shift, how do we find it? If we are on the second case, how do we find the period? So okay, so I don't have time to see how we handle all these challenges, but this incurs like extra order of TQ samples. So that is where our running time comes from. We have the sample set, which is of size n over t, plus these t cube things to handle these challenges. So let me just conclude. So what was our main theorem? We proved that there is an algorithm solving the t versus t square gap in time n over t plus t cube. If we want to solve a better gap, like if we want to increase the gap a bit and not t versus t square, but t versus t square minus epsilon, then we can do it in the cost of having like more samples. And let me conclude by some open problems. So if we focus just on the t versus t square gap, so the first open question is, can we break this t cube barrier? The other thing is, can we break the n over 2 barrier? Because the current lower bound is just n over t square, which is null for Hamming. So maybe the right barrier should be n over t square plus t cube. If we focus on a much smaller gap, like t versus c times t, can we do it in n over t plus some poly t? If we can't do it, can we prove a lower bound? So these are all the open questions I had. Thank you.
Any questions? Yeah.
Roughly speaking, it seems that if you increase the value of t, the problem will only become easier. On the other hand, you have this additive TQ term. Is there any intuition as to why the problem becomes harder as t becomes larger?
So the problem, like if you think of it if you think of solving the exact problem, yes? So then, like if t is very small, if t is square root of n, then you have a linear time algorithm. If t becomes larger, then you're going to the strong ETH, you are going to the n square algorithms. So this is a rough intuition why this is a harder regime.
Let's thank the speaker again.